study unit is devoted to priority control. In this unit, we will cover the concepts that permit bus requests to be handled in an orderly and efficient manner. Let's begin by reviewing a few key points. As we said before, a bus cycle is the smallest task a PDP-11 system can perform. It is used whenever two devices communicate by means of the unibus. We also said that one instruction cycle is composed of one or more bus cycles. In this example, the instruction involves 4 bus cycles. In order to perform a bus cycle, a device must first request the bus. Remember, there are 2 methods of requesting bus control. A device makes a non-processor request, or NPR, if it wishes to use the bus to perform a data transaction that does not require processor intervention. On the other hand, if the device needs the bus to interrupt the CPU for help, it makes a bus request, or BR. The priority control honors an NPR or BR by issuing a corresponding grant, either an NPG or a BG. When an NPR request has been made and honored, the device can take over the bus between bus cycles. In other words, a device can perform bus cycles of its own between bus cycles of an instruction. On the other hand, when a BR has been issued and honored, the device can take over the bus only upon completion of the current instruction cycle. Thus, the device cannot interrupt the processor while an instruction is being executed. Now that we have reviewed some basic concepts, let's see what will be covered in this study unit. This study unit is divided into 2 major sections: priority structure and priority arbitration. The first section, priority structure, is further divided into 3 main topics: vertical priority, horizontal priority, and priority assignments. Let's start out by looking at the vertical priority levels used in PDP-11 systems. In the PDP-11 system, we have 5 vertical priority levels decreasing in priority from the top level to the bottom. In this setup, a requesting device on one priority level is serviced before any lower level is handled. Now, let's examine each of these priority levels, beginning with the NPR level. There are 4 key points we want to mention about the NPR level. First of all, it has the highest priority of any of the 5 levels. Secondly, an NPR request is honored between bus cycles of an instruction. Therefore, the device does not have to wait for completion of an instruction before taking over the bus. Performing operations between bus cycles of an instruction is often called cycle stealing. The NPR level is used for obtaining the bus to perform data transactions involving direct memory access, or DMA transfers. In other words, some bus devices can interact with memory without help from the processor, which brings us to the final key point. The NPR level does not involve the CPU. When a device gains bus control by means of an NPR, it performs its task without processor intervention. Now, let's see how bus requests at the NPR level are honored. There are actually 2 lines associated with the NPR priority level. When a device wants to use the bus, it issues a request by means of the NPR, or non-processor request line. The priority control receives the request and responds by issuing a grant on the NPG, or non-processor grant line. That's basically how NPRs are honored. Now, let's take a look at the other 4 priority levels that we mentioned before. The other priority levels are called BR levels and are numbered 4 through 7. BR7 has the highest priority and BR4 has the lowest priority, which ties in with our earlier statement that the highest priority is always at the top. Let's talk about some of the key points associated with these BR levels. First of all, a request at the BR level is honored only between instruction cycles. Unlike NPRs, when a device issues a BR, it must wait for the current instruction to be completed before its bus request can be honored. Secondly, the BR levels are used for interrupts. In other words, the device wants the bus so that it can obtain help from the processor. Which brings us to the last point. Any request made on a BR level requires processor intervention. By the way, that's why BRs are honored between instructions. Because we're going to interrupt the processor's job, we want to let it finish its current instruction first. Now, let's look at the way BR requests are honored. The BRs are similar to NPRs in that there are two lines associated with each BR level. Assume a device on level BR7 wants to use the bus. It issues the request by means of the BR7 line. If the priority of the bus request is greater than the priority currently assigned to the CPU, the priority control responds by issuing a bus grant signal on the BG7 line. Each priority level has a BR, or bus request line, and a BG, or bus grant line. Now, let's combine all priority levels into one chart. Here's our complete structure of device priority levels. Notice how priority increases as we proceed upward. The BR4 level has the lowest priority, the BR7 level has the highest priority for BR levels, and the NPR level, which is used by DMA devices, has the highest priority in the entire structure. In addition to these device priority levels, we can set the CPU to any one of 8 priority levels. Note that the CPU's priority is not fixed. Its priority level can be raised or lowered by the program that is running. For example, the CPU's priority can be elevated from level 4 to level 6. Such changes in priority occur when the CPU stops executing one device service routine and then begins executing a higher priority routine. You can see what flexibility this gives us. We can use the CPU's priority to block out or mask bus requests from devices at the same priority level or at lower levels. For example, when the CPU's priority is set to level 6, all bus requests appearing on BR4, BR5, and BR6 are ignored. This allows the CPU to hold off servicing lower priority tasks until the more critical tasks are completed. Horizontal priority adds a second dimension to our two-dimensional priority system. Because there are only 5 priority levels, it's often necessary to connect more than one device to a level. In this example, we have 11 devices. 3 are connected to the NPR level, 1 to the BR7 level, 2 to the BR6 level, and so on. When a number of devices are connected to the same priority level, it is referred to as horizontal priority. If more than one device is making a request on any NPR or BR level, the device closest to the priority control has the highest priority. As you can see here, the NPR device next to the priority control has first priority. The device farthest away has the third or lowest priority. As we noted earlier, there are actually 2 lines associated with each priority level. For example, all devices at the NPR level submit their bus requests to the priority control over the NPR line. The priority control, in turn, issues a bus grant over the NPG line. Notice that the NPG line is connected to all 3 devices in a daisy chain arrangement. In effect, the NPG line passes through each device. Let's see how this chaining arrangement relates to horizontal priority. In this example, only the second NPR device on the bus has issued a bus request. This request, which says, "I need bus control," is sent to the priority control on the NPR line. The priority control responds by sending the request granted signal along the NPG line. This grant signal travels along the NPG chain, passing through any non-requesting devices, and is captured by the first device requesting the bus. In this case, it's the second device in the chain. Once this device captures the grant signal, it prevents it from traveling any further. Therefore, requesting devices further away from priority control will not receive this particular grant. As you can see from this chaining example, horizontal priority depends on how close the device is to the priority control. The closest device has first choice of capturing the bus grant. The second device has next choice if the first device doesn't capture the grant, and so on. Now, let's look at BR chaining. The method of BR chaining is identical to that at the NPR level. However, note that each BR level has its own independent grant, or BG chain. For example, the grant chain for the BR7 level is the BG7 line, which is chained through all devices at the BR7 level. At this point, let's put everything together and look at our two-dimensional priority structure. Here we see both the vertical and horizontal priorities in a typical PDP-11 system. Note that the lowest vertical priority level is BR4 and the highest priority level is NPR. Horizontal priority is dependent on distance. The device closest to the priority control has the highest priority at that level. The device furthest away has the lowest priority. Now that you understand the priority structure, we're going to discuss devices that require more than one priority level. A direct memory access, or DMA device, operates at both an NPR and a BR level. The device uses the NPR level to perform data transactions that do not involve the CPU. However, on occasion, the DMA device may also need to interrupt the CPU. Hence, the DMA device also operates at one of the 4 BR levels. Here we see a typical DMA device, such as a DEC tape, mag tape, or disk. When it needs the bus for a DMA data transaction, it makes an NPR request and receives an NPG grant from the priority control. On the other hand, if it needs to interrupt the processor, it makes a request on the BR line and receives a grant on the corresponding BG line. That completes our discussion of vertical and horizontal priority. Now, let's look at priority assignments. When deciding where to assign a device in the priority structure, there are 3 factors that should be considered. The first factor is the operating speed of the device. This speed determines how long data is available for a transfer before it is lost. The next factor that must be considered is data recovery. In other words, if the data is lost for some reason, can it be recovered? And if so, how difficult is the task of retrieving the data? How long will it take? The final item to be considered when assigning priorities is the service requirements of the device. These requirements are directly related to how much help the device normally needs from the processor. Now we're going to explain each one of these 3 factors in more detail and then show you some typical PDP-11 priority assignments. When a fast device, in this case a disk, performs a transfer, the data is available for a relatively short period of time. The device receiving the data, in this case memory, must strobe in the data within this time frame or window. If it doesn't, then the data will be lost. With a slower device, such as a DEC tape, we have more time to strobe in the data. Therefore, faster devices should have a higher priority to make sure they can obtain the bus in time to transfer the available data. Another factor used in determining priorities is the ease of data recovery. If data is lost from a disk, recovery is simple and virtually automatic. The lost data can be picked up during the next disk revolution. If data is lost from a card reader, manual intervention is required to reload the cards. The cards can then be reread in order to recover the lost data. If data is lost from an analog to digital converter, it cannot be recovered because this device is sampling real-time data. As you can see from these examples, the highest priority should be given to the device that does not permit recovery of data, in this case, the analog to digital converter. The lower priorities should be assigned to devices that can recover data easily. This brings us to our third and final factor. The service requirements of a device also determine its priority assignment. At the left, we have a line printer which cannot operate without help from the processor. The printer must continually request help by means of interrupts, and the processor responds by managing all line printer operations. At the right, we have a disk, which is capable of transferring blocks of data to memory without help from the processor. Normally, the disk interrupts the processor only after it has completed its transfer or has terminated operation due to an error condition. Because of these different service requirements, we typically assign a low priority to the line printer and a higher priority to the disk. If we didn't, the processor would be tied up servicing the line printer, while devices requiring minimal help from the processor, such as the disk, would not be able to get the processor when they need it. We have shown that priority assignments are determined by three factors: operating speed, ease of data recovery, and service requirements. Now we're going to look at some typical PDP-11 device priorities and analyze them one by one to show you why a specific priority level was chosen. These are the 8 devices that we will discuss. Notice that we are only interested in the BR levels at this point. We'll get into the NPR level later. Don't try to remember everything on this chart. There's a copy included in your workbook. Besides, we're going to talk about each one of these items separately. We'll start with the analog to digital converter. The analog to digital converter is placed at the BR7 level because we're assuming that it must sample data which has a high input rate. The A to D converter is a fast device sampling real-time data which is lost completely if a sample is missed because there's no way of recovering it. Therefore, we assign a high priority to make sure the converter gets the bus right away to handle each sample before it is lost. If, on the other hand, the data being sampled was arriving at a very slow rate, we could assign a lower priority because the chance of losing data would be less. Now, let's go to the next BR level. We have 2 devices at the BR6 level, a line clock and a deck tape. The line clock divides time into specific intervals for more efficient use of PDP-11 computer time. One of its functions is to interrupt the processor after a specified number of time intervals have elapsed. Therefore, the clock must have a relatively high priority so that its interrupt can be serviced immediately. Otherwise, there's no point in using a clock. The deck tape is also placed at the BR6 level because it transfers short blocks of data, thereby requiring moderate processor intervention. Now, let's look at the next level. The 2 units at the BR5 level are a disk and a magnetic tape unit. You may wonder why the disk and magnetic tape unit are at a low priority level when they are both fast devices with minimum service requirements. Well, both devices normally perform data transfers at an NPR level, which is the highest priority. However, they also require a BR level so that they can request new commands or inform the processor of an error condition. Because the disk and mag tape perform long data transfers, they do not need new commands often. Therefore, on an interrupt or BR basis, they can have a lower BR priority than a device such as the A to D converter that relies solely on interrupts for servicing. Now, let's look at the lowest device priority level. Here we've shown 3 units at the BR4 level: a deck writer, a paper tape reader punch, and a line printer. All 3 of these devices are at the lowest priority level because of 2 main reasons. First of all, they are relatively slow devices. Secondly, they are likely to interrupt the processor more often than the other devices and would tend to tie up the bus if they were placed at higher priority levels. At this point, we might mention the horizontal priority of these 3 devices. The deck writer is closest to the priority control and therefore has the highest horizontal priority of the 3. We do this because the deck writer is our system I/O device. The reader punch is next because it is also used as a system loading and reading device. The line printer has the lowest priority of the 3. Now, let's take a look at the devices that are assigned to the NPR level. We mentioned previously that the deck tape, disk, and mag tape all had interrupt capabilities, but were primarily DMA devices. That is, they perform direct memory access data transfers without processor intervention. As you know, bus requests for DMA transfers can only be made at the NPR level. Let's see how NPR priorities are assigned to these 3 DMA devices. The factor that determines priorities at the NPR level is the time the data is available. Here we see data availability times for 5 types of devices. You can see, for example, that data from a disk is available for a very short period of time compared with the data from a card reader. In order to prevent loss of data, we must service a device within the time its data is available. For this reason, we assign the highest NPR priority to the device with the shortest data available span, and the lowest priority to the device with the longest span. Remember our 3 DMA devices, disk, magtape, and deck tape? Well, based on this chart, our priority assignments should be disk first, magtape second, and deck tape third. Now, let's add the NPR line and the DMA devices to our example. As you can see, we assigned NPR priorities to the 3 DMA devices in the order we just mentioned: disk, then magtape, and finally deck tape. Notice that the factor determining the NPR priority differed from the factors used in assigning BR priorities. Thus, the disk has the highest NPR priority, but the deck tape has the highest BR priority. At this point, let's briefly review our entire priority structure. The PDP-11 has a 2-dimensional priority structure to handle all bus devices. One dimension is vertical, and priorities are dependent on the level to which a device is connected. There are 5 levels, 1 NPR level and 4 BR levels. The second dimension in our priority structure is horizontal, and priorities are dependent on how close the device is to the priority control. Thus, any device in a PDP-11 system has a prime or vertical priority and a secondary or horizontal priority. The CPU is also part of this priority system. However, its priority can be modified by a program, whereas the device priorities are fixed. We can use the CPU's priority to block out or mask bus requests at any of the 4 BR levels. This permits interrupts only on those lines whose priority level is greater than that of the processor. We'll have more to say about the CPU's priority in a later study unit. The main factors determining assignment of priorities are operating speed of the device, which includes the time data is available, ease of data recovery, and the device's dependency on the processor for service. Based on the factors just mentioned, we assign a specific priority level to each device in our PDP-11 system. Here we see some typical priority assignments. Notice that DMA devices normally have both a BR level and an NPR level assigned. In the right-hand portion of our chart, we've indicated the horizontal priorities assigned to devices at the NPR level. That wraps up our discussion of the PDP-11 priority structure. Now we're going to look at priority arbitration. All request and grant lines, NPR, NPG, BRs, and BGs, connect to the priority arbitration logic. Remember that we may have a number of devices on the Unibus, each with its own priority. When more than one device wants the bus, we must have a way of deciding who gets the bus, based on our priority structure. That's one purpose of the priority arbitration logic. It acts as an arbitrator, or umpire, when more than one device requests the bus at the same time. For example, when a BR7 device and a BR6 device are contending for the bus, the umpire, or PA, awards the grant to the higher priority device, and in this case it calls for a BG7 grant. Notice that the priority arbitration logic, or PA for short, resides in the CPU. However, it is electrically divorced from the CPU. In other words, as far as the PA is concerned, the CPU is another bus device, with one important exception. Whenever no one else wants the bus, control automatically reverts to the CPU. The PA logic monitors all bus requests. It determines which device is to become bus master based on the priority structure, and then grants bus control by issuing an NPG or BG signal. Let's see what happens when 2 devices make a simultaneous bus request. Assume a BR7 and a BR6 device are making bus requests at the same time. These 2 requests enter the PA logic, which acts as the umpire. If the CPU is currently operating at a lower priority level, for example BR5, the PA issues a BG7, thereby granting the bus to the higher priority device, our BR7 device. Notice that the lower priority device keeps its BR6 request up. The BR7 device issues SAC while waiting for the bus. As soon as the bus is free, the device asserts bus busy and drops SAC. At this instant, something happens to both devices. When the BR7 device drops SAC and asserts bus busy, the PA is again free to act as an umpire. As a result, the BR6 device has its request granted. It then asserts SAC and waits for the bus while the BR7 device is using the bus to issue an interrupt. At this point, we're going to briefly review the main topics we've covered and then show you two examples tying everything together. There are 5 different priority levels. The NPR level has highest priority, BR7 the next highest, and so on. BR4 is the lowest priority level. The highest priorities are generally assigned to devices requiring fast service in order to prevent loss of data. In this case, the disk and A to D converter have the highest priorities. Lower priorities are assigned to slower devices that can afford to wait for service, such as the deck writer. Notice that DMA devices, such as the disk, are assigned to 2 levels. The NPR level is used by the disk to perform data transactions without processor intervention. The disk also has a BR level assigned so that it can interrupt the processor in the event it needs to be serviced. Horizontal priority adds a second dimension to our priority structure. In other words, devices electrically closest to the priority control have the highest priority of any device at that level. Thus, on the NPR level, the disk has the highest priority, the deck tape has the lowest. Now, let's review one final point. Bus operations can be overlapped. That is, priority arbitration can be performed in parallel with an interrupt or a data transaction. As you can see, device A has the higher priority and its request was granted before the BR5 request. However, as soon as device A asserts BBSY and takes over the bus, the BR5 request is honored by a BG5 grant. Device B now asserts SAC and then waits for device A to give up the bus. As soon as device A is finished with its transfer, device B immediately assumes bus control by asserting BBSY. There is no time lag when passing bus control from one device to another. That wraps up our review, so let's look at 2 examples of priority arbitration. In our first example, we're going to assume that 2 devices at different priority levels both request the bus at the same time. Here, we see an analog to digital converter making a bus request at the BR7 level and a deck tape making a simultaneous request at the BR6 level. Both requests enter the priority control, which must decide who gets the bus. The priority control recognizes BR7 as the higher priority and sends a grant on the BG7 line to the A to D converter. Notice that the deck tape does not give up. It continues sending its BR6 request to the priority control. Let's see what happens next. At this point, the A to D converter drops its bus request and asserts SAC while waiting for the bus to become free. This signal ensures that the A to D converter gets the bus next. The deck tape still hasn't given up. It maintains its BR6 request. Let's see why. As soon as the bus is free, the A to D converter drops SAC, asserts bus busy, and takes over. Remember now, it keeps bus busy asserted as long as it uses the bus, which can never be longer than 1 bus cycle. The A to D converter has also cleared SAC. This is just what the deck tape has been waiting for. With SAC cleared, the priority control recognizes the deck tape's request and honors it by issuing a grant on the BG6 line. That finishes this example. Let's look at one more before we wrap up this study unit. In this final example, we are going to assume that 2 devices at the same priority level both request the bus at the same time. Here we see 2 devices, a disk and a mag tape, both in contention for the bus. Their requests are made at the same level. The priority control does not distinguish between the requests. All it knows is that the BR5 request line is active. If the CPU is operating at a lower priority level, the priority control acknowledges the BR5 request by placing a grant signal on the BG5 line. Because the disk is closest to the priority control, it gets first chance at the signal. And because the disk has made a request, it captures the grant, preventing it from going any further. Let's see what the disk does now. The disk now asserts SAC to let everyone know that it is the next bus master. It also drops its bus request because it has now been honored. The MagTape, meanwhile, continues to assert its BR5 request. Because the BR5 request line is still active, the priority control again issues a grant on the BG5 line. This grant reaches the disk, which now has no need of it. It has already dropped SAC and asserted bus busy and is engaged in its bus cycle. Therefore, the grant signal is released and goes to the second device. The second device didn't make a request, so it refuses the grant signal, which travels along the chain until it reaches the MagTape. As soon as the grant reaches the MagTape, the device grabs it. At this point, the MagTape's request has been honored, and it will get the bus next. Well, we're finished with this study unit. It's time for another test. Remember now, this test is self-scoring and is intended only for your use. Based on the test results, either review the material in this study unit or proceed to the next study unit. When you hear the next tone, turn off this playback unit and take the test located in your workbook.